Hi, topic for today's session will be on brief introduction to transformers. This session is part of Introduction to NLP for Data Science course. I'm Hari, Associate Instructor for this course. Now let's get started. In 2017, researchers at Google published a paper that proposed a novel neural network architecture for sequence modeling called Transformer, which outperformed RNNs, which stands for Recurrent Neural Networks, on machine translation tasks, both in terms of translation quality and training cost. In parallel, an effective transfer learning method called ULMFIT, which stands for Universal Language Model Fine Tuning, showed that training LSTM, which stands for Long Short Term Memory Networks, on a very large and diverse corpus could produce state of the art text classifiers with little labeled data. These advances were the catalyst for two of today's most well-known transformers, GPT, which stands for Generative Pre-trained Transformer, and BERT, which stands for Bidirectional Encoder Representation from Transformers. By combining the transformer architecture with unsupervised learning, the these removed the need to train task-specific architectures from scratch and broke almost every benchmark in NLP by a significant margin. Since the release of GPT and BERT, a zoo of transformers models has emerged. Our timeline of most prominent entries is shown here. To understand what is novel about transformers, we need to understand following core concepts that underlie the pervasiveness of transformers. The, to begin with, the encoder-decoder framework. Recurrent architectures such as LSTMs contain a feedback loop in the network connection that allows information to propagate from one step to another, making them ideal for modeling sequential data like text. As illustrated in the figure, an RNN receives some input, feeds it through the network, and outputs a vector called hidden state. At the same time, RNN passes information about its state at each step to the next operation in the sequence. This way, the model keeps track of information. RNNs played an important role in the development of machine translation systems, where the objective is to map a sequence of words in one language to another. This kind of task is usually tackled with an encoder-decoder or a sequence-to-sequence architecture, which is well suited for situations where the input and output are both sequences of arbitrary length. The job of the encoder is to encode the information from the input sequence into a numerical representation that is often called the last hidden state. The state is then passed to the decoder, which generates the output sequence. In general, the encoder and decoder components can be any kind of neural network architecture that can model sequences. Drawbacks of this framework: although elegant in its simplicity, one weakness of this architecture is that the final hidden state of the encoder creates an information bottleneck. It has to compress and represent the meaning of the whole input sequence because this is all the decoder has access to when generating the output. This is especially challenging for long sequences where information at the start of the sequence might be lost in the process of compressing everything to a single fixed representation. Fortunately, there is a way out of this bottleneck by allowing the decoder to have access to all of the encoder's hidden states. The general mechanism for this is called attention, and it is a key component in many modern neural network architectures. Understanding how attention was developed for RNNs will put us in a good shape to understand one of the main building blocks of the transformer architecture. Let's take a deeper look. The main idea behind attention is that instead of producing a single hidden state for the input sequence, the encoder outputs a hidden state at each step the decoder can access. However, using all the states at the same time would create a huge input for the decoder. So some mechanism is needed to prioritize which states to use. This is where attention comes in. It lets the decoder assign a different amount of weight or attention to each of the encoder states at every decoding time step. This process is illustrated in the figure, where the role of attention is shown for predicting the third token in the output sequence. By focusing on which input tokens are most relevant at each time step, these attention-based models are able to learn non-trivial alignments between the words in a generated translation and those in a source sentence. For example, figure visualizes the attention weights for an English to French translation model where each pixel denotes a weight. The figure shows how the decoder is able to correctly align the words zone and area, which are ordered differently in two languages. Although attention enabled the production of much better translations, there was still a major shortcoming with using recurrent models for the encoder and decoder. The computations are inherently sequential and cannot be parallelized across the input sequence. With the transformer, a new modeling paradigm was introduced. Dispense with recurrence altogether and instead rely entirely on a special form of attention called self-attention. The basic idea is to allow attention to operate on all states in the same layer of the neural network. This is shown in the figure, where both the encoder and the decoder have their own self-attention mechanisms, whose outputs are fed to feed forward neural networks, with, which is displayed as FF and N in the figure. This architecture can be trained much faster than the recurrent models and paved the way for many of the recent breakthroughs in NLP. In the original Transformer paper, the translation model was trained from scratch on a large corpus of sentence pairs in various languages. However, in many practical applications of NLP, we do not have access to large amounts of labeled text data to train our model on. A final piece was missing to get the transformer revolution started, which is called the transfer learning. In simple words, transfer learning is knowledge gained while solving one problem and applying it to a different but related problem. Architecturally, this involves splitting the model into a body and a head, where the head is a task-specific network. During training, the weights of the body learn broad features of the source domain, and these weights are used to initialize a new model for the new task. Compared to traditional supervised learning, this approach typically produces high-quality models that can be trained much more efficiently on a variety of downstream tasks and with much less labeled data. Although transfer learning became the standard approach in computer vision, for many years it was not clear what the analogous pre-training process was for NLP. As a result, NLP applications typically required large amounts of labeled data to achieve high performance. And even then, the performance did not compare to what was achieved in vision domain. ULIMFIT introduced a general framework to adapt pre-trained LSTM models to various tasks. As illustrated in the figure, ULIMFIT involves three main steps. Pre-training. Here, the initial training objective is quite simple. Predict the next word based on the previous words. This task is referred to as language modeling. The elegance of this approach lies in the fact that no label data is required and one can make use of abundantly available text from sources such as Wikipedia. Second step, domain adaptation. Once the language model is pre-trained on a large-scale corpus, the next step is to adapt it to the in-domain corpus. For example, from Wikipedia to IMDb corpus for movie reviews, as shown in the figure. This stage still uses language modeling, but now the model has to predict the next word in the target corpus. Step number 3 is fine-tuning. In this step, the language model is fine-tuned with a classification layer for target task. For example, classifying the sentiment of a movie review. In 2018, two transformers were released that combined self-attention and transfer learning. Those are GPT and BERT. Now let's just have some examples and just switching to the notebook now. I'll be using Hugging Face transformers in this demo. The Hugging Face transformers provide a standardized interface to a wide range of transformer models, as well as code and tools to adapt these models to new use cases. The library currently supports three major deep learning frameworks, PyTorch, TensorFlow, and JAX, and allows you to easily switch between them. In addition, it provides task-specific heads so you can easily fine-tune transformers on a downstream task, such as text classification, named entity recognition, question answering, etc. This reduces the time it takes a practitioner to train and test a handful of models. Let's say this is the text I'll be using for this demo. It's about Amazon review. Let me start with the text classification pipeline. So the pipelines are a great and easy way to use models for inference. These pipelines are objects that abstract most of the complex code from the library, offering a simple API dedicated to several tasks, including name entity recognition, masked language modeling, sentiment analysis, etc. Classifier is a text classification object here. Classifier is a text classification object here. And here are the transformer labels. The given text input as a negative with a score or the probability of 0.09. Next, named entity recognition. Selecting NER pipeline, and these are the words that the model was able to tag from the given text. These are the corresponding entity groups and scores. Start and end are the indexes of a tagged word in a given text, also called as a span of a word. Next is question answering. Again, selecting question answering pipeline, and the question provided is, what does the customer want? Inputs to the model are the question and the context, which is the text variable here. And the model outputs the answer for the given question as an exchange for Megatron, which is exactly what the customer is asking for. Moving on to summarization, again selecting summarization pipeline, and this is the summary that model produced. Next, moving on to translation, selecting translation from English to German from the pipeline, and this is what the model generated German translation for this given text. And finally, the last pipeline for this demo is text generation. This is the initial response on which the model expands or generates further response. This is a prompt or text followed by some text followed by initial response. Setting up the maximum length to generate 200 characters, and here is the output. Initial response, and this is the generated response based on the given prompt. This is all for this demo. I hope you got an overview of what transformers are and what they are capable of. Try them for yourself and see why they are game changers in NLP.